Hi everyone, in today's video we're going to continue our discussion on alcohols. This time we're going to focus on the preparation of alcohols, and then before we go into our last reaction we're going to introduce the concept of an oxidation state, because the series of reactions we're going to focus on can be classified as redox reactions involving alcohols. It's my hope that by the end of this video, you'll be able to prepare alcohols from substitution and addition reactions that you have learned in the past, and then also a new reaction called a reduction that you're going to learn for the first time here in this video. You'll also be able to determine the oxidation states of atoms in organic molecules, as well as predict when an oxidation state has changed between molecules. You'd be able to propose simplified mechanisms for reduction of carbonyl compounds to alcohols, and then in a synthesis format, predict the products and propose reagents for alcohol oxidations to aldehydes, ketones, and carboxylic acids. Okay, so there are three main methods in which we can prepare alcohols. We can either do that through substitution and addition chemistry, we can do that through reduction chemistry, and then lastly, we can do that through dihydroxylation chemistry. So we're going to start with substitution and additions. Regards to substitution, recall that alkyl halides can be converted to alcohols via SN1 or SN2 chemistry. For example, if we take this primary alkyl halide and you treat that primary alkyl halide with sodium hydroxide, hydroxide being a strong nucleophile, strong base, the mechanism that this reaction would undergo is through an SN2 mechanism to form this alcohol, in this case a propanol, and your byproduct will simply be your sodium chloride salt. On the other hand, if you take this tertiary alkyl halide, you can react that tertiary alkyl halide now with a weak nucleophile, weak base, because you want to avoid Na elimination. So instead of sodium hydroxide, you want to use water in this case. And through SN1 pathway, you're going to substitute out that chlorine with an OH group and then form HCl as your byproduct. So recall once again from previous chapters that alkenes can undergo hydrations to be converted into alcohols. But in all of these cases, you're essentially getting alcohols, you're preparing alcohols through addition chemistry on an alkene. You can also prepare alcohols via reduction of carbonyl compounds. But before we go into this particular reaction, we have to properly understand oxidation and reduction. And to do that, we need to review oxidation states. So oxidation states is actually another way to do what we call electron bookkeeping. In this system of electron bookkeeping, all bonds within a molecule are treated as purely ionic. This means that when doing your electron counting and accounting for where electrons are, you want to separate out a bond in a heterolytic manner where the bonding electrons move to the more electronegative atom. And from there, you can actually then assign oxidation states to every single atom within an organic molecule. Let's do an example. And for this example, we're going to consider methanol, so CH3OH. And what we're going to ask is, what is the oxidation state of the carbon atom in methanol? So at some point, you're going to get a good handle on how to assign this very easily. But for now, what you want to do is explicitly show all the bonds to that particular carbon that you're trying to assign an oxidation state to. So now if we treat all of the bonds as purely ionic, then in order to assign oxidation states, we have to give those bonding electrons to the atom that is more electronegative. So what this is going to mean is, for all three of those CH bonds, because carbon is more electronegative than hydrogen, to assign oxidation states, one needs to think about those two electrons within the single bond being attached to really just the carbon, which would make the ionic nature be H plus and C minus. And that would mean that carbon would have incurred an oxidation state of -3 from those three hydrogens. However, carbon is also bonded to one oxygen through a single bond. And because oxygen is more electronegative than carbon, that CO bond treated as ionic would actually place a positive charge on the carbon and a negative charge on the oxygen. And so if you sum up all the charges around that carbon, the oxidation state of that carbon in methanol is going to be -2. So using that same method and completing this entire thing for methanol, what you want to do on your own is to determine the oxidation state for each of the hydrogen atoms in methanol, as well as the oxygen atom in methanol. So just keep going with this particular analysis on your own. However, because carbon is very versatile, the oxidation states of carbon atoms in a variety of organic molecules can actually range dramatically from -4 all the way to +4. So let me show you some examples of molecules with carbon atoms that have oxidation states across the spectrum. So consider methane. If you do that same analysis as we did for methanol, the central carbon in methane is going to have an oxidation state of -4. We've established that for methanol, the oxidation state of that carbon is -2. And then for formaldehyde, the oxidation state of that central carbon is actually equal to 0. For your formic acid, that central carbon has an oxidation state of +2. And then lastly, for carbon dioxide, that central carbon has an oxidation state of +4. So note a couple of things here. As you increase the number of bonds to oxygen from a carbon, the oxidation state tends to increase. And then likewise, if you reduce the number of hydrogens bonded to a carbon, the oxidation state of that carbon also tends to increase. And this is really just because of the electronegativity difference between carbon and then these two atoms, hydrogen and oxygen. In our last discussion of determining oxidation states, what I want us to do is determine the oxidation state of the central carbon atom in 2-propanol, and that's the carbon that I have starred on the screen. If you draw out all atoms explicitly, you will see that that central carbon is bonded to two carbons, one hydrogen and then one oxygen. For the bond between the carbon and the hydrogen, because carbon is more electronegative than hydrogen, it's going to take all those electrons from that bonding electron and you're going to assign that to carbon. So you can have a negative charge on that carbon, a positive charge on the hydrogen. And then between the carbon-oxygen bond, because oxygen is more electronegative than carbon, those two electrons are going to move towards the oxygen, which will put a negative charge on the oxygen and a positive charge on the carbon. However, on the CC bond end, because there is no difference in electronegativity between the atoms, we assume that one electron is going to go to one carbon and then the other electron is going to go to the other carbon. And then the same goes for the CC bond on the right-hand side. This is going to mean that the oxidation state will be the net sum of those charges around the carbon, and in this case it's going to be 0 because the positive charge is going to cancel out the negative charge. So the oxidation state at that carbon is equal to 0. Okay, so you should be able to assign oxidation states to different atoms, and that would help us know if a redox reaction has happened. In other words, if oxidation or reduction has happened around a carbon, we can actually do the accounting by doing this type of like analysis. Okay, so now that we've talked about oxidation states, now let's focus on reactions that involve a change in the oxidation state of a molecule. So recall from general chemistry that oxidation reactions are reactions that result in an increased oxidation state, and reduction reactions are reactions that result in a decreased oxidation state of a molecule. But our focus is going to be on reductions to prepare alcohols. So the first type of reduction we're going to really focus on is the reduction of a ketone or an aldehyde to an alcohol. In order to do this, we need to use a reducing agent to make this work. And then convince yourself that the central carbon that is bonded to the oxygen is reducing from +2 to 0 in this particular reaction. And there are three major reducing agents that we typically use in organic chemistry. The first one is using hydrogen gas in the presence of a metal catalyst. So in a very similar fashion to an alkene, if you take a ketone or an aldehyde and you treat it with H2 gas in the presence of a platinum catalyst or a palladium catalyst or a nickel catalyst, you end up with the reduced product. So that's you're going to end up with the alcohol in this case. Note that in this case, you typically have to do this reaction under high temperatures and high pressures. And this reaction is not selective for just ketones and aldehydes. Remember that if you take the same reagents, you would also reduce alkenes and alkynes down to alkanes. So be very careful about that from a synthetic point of view. The second method, which is arguably much better from a synthetic point of view because it's milder and it is selective, is to use sodium borohydride, which is a very common reducing agent. So if you treat your ketone or an aldehyde with sodium borohydride, and you have to make sure that you are in an alcoholic solvent such as methanol or ethanol or even water, if you do so, you will get the reduced alcohol 2-propanol. So note in this case that the hydrogen that adds to the carbon actually comes from the borohydride, and then the hydrogen that adds to the oxygen comes from the solvent itself. So let's propose a mechanism for this reaction. Okay, so you start your reaction with your aldehyde or a ketone, and you're going to react that with your borohydride species. One caveat before we move forward is that this mechanism is actually dramatically simplified. We know that the sodium is actually important to this reaction, but we're not showing the role of the sodium here. We're simply just looking at the anion of the borohydride. The borohydride actually acts as a nucleophile, which delivers an H minus to the electrophilic portion of your aldehyde or your ketone, which in this case is the carbonyl carbon. And so the first step is a nucleophilic attack of like an H minus like species at your carbonyl carbon, which then produces your alkoxide species if you're following your arrow push in. And then in your second step, your alkoxide can then deprotonate the solvent molecules, so it could be ethanol, methanol, or water, in a proton transfer step to form your alcohol. Your third option is to use what we call lithium aluminum hydride, or LiAlH4, or a short form LAH. And it's a very strong reducing agent that actually acts very similar to sodium borohydride. And so if you treat your ketone or aldehyde with lithium aluminum hydride, and then you do your wash in H2O, you will get your alcohol as well. And once again, the reaction is very similar to the NaBH4. But note that unlike the sodium borohydride reducing agent, we need to do this lithium aluminum hydride base reduction in two steps. So we actually cannot place lithium aluminum hydride in the presence of water because lithium aluminum hydride was going to react pretty violently with water. And so that's why we need to actually do this in two separate flasks, where we first treat it with lithium aluminum hydride, we form our alkoxide species, and then in a different flask, we can then wash our products with water. So other carbonyl containing compounds can also be reduced to prepare alcohols. So you can reduce a carboxylic acid or an ester to an alcohol form. However, in these cases, excess lithium aluminum hydride is needed for these reactions. So if you take this carboxylic acid and you treat it with excess lithium aluminum hydride, and then you treat it with water as a second flask, you will get the alcohol of that carboxylic acid, and then also water would be released in this flask. But that's not a very important product since our solvent in the last flask is also water. In the same vein, you can take an ester, which is kind of like your carboxylic acid, except at the OH group, you have an OR group. So you take your ester and you react that once again with excess lithium aluminum hydride, and then you treat it with water. In this case, you actually get two alcohols. So you might see from the pattern that the mechanism for both of these reactions is probably going to be very, very, very similar. So let's look at the mechanism. Once again, it's going to be simplified for ester reduction, and then we're going to use that to sort of think about the mechanisms of all these types of reactions. So the aluminum hydride is very similar to the borohydride in the sense that you simply have either aluminum or boron in the middle of four different hydrogens. But in the very same vein, that borohydride is a nucleophile, which basically produces an H minus as a nucleophile. The aluminum hydride does a very similar reaction. So you go through a nucleophilic attack and you get to this really high energy intermediate. So this is a tetrahedrocarbon with two oxygens bonded to it. So you can imagine that's going to be pretty high energy. And so the next step here is going to be the loss of a leaving group, which will then release your OR group from that carbon-based fragment, and you're going to form an aldehyde in this step. But keep in mind that the aldehyde is still not the most reduced form. We can get down to an alcohol. And we've seen this mechanism before in the previous scene. An aldehyde in the presence of a reducing agent such as aluminum hydride, which you have in excess in this flask, can also go through another nucleophilic attack to form now your other alkoxide. And now you're going to accumulate all of these alkoxides in your flask until you completely reduce all of your esters. Okay, so now we're done with synthetic step one. Now we can then wash both of our products in water. And essentially, you're going to go through multiple proton transfer steps that get you to your desired product. Okay, so note that in this case, it's a nucleophilic attack on that carbonyl carbon. You form that high energy intermediate. You go through a loss of a leaving group, which will produce one of the alkoxide products, but then also produce an aldehyde. Another aluminum hydride can come in, attack, nucleophilically attack that carbonyl. You form your second alkoxide, and then once you get to this point, you're going to finish that first synthetic step, and then you can then wash both of your alkoxide products with water to then form the protonated alcohols in your flask. Okay, so that's how you can prepare your alcohols through reduction chemistry, but from an aldehyde ketone perspective or from a carboxylic acid or an ester perspective. And then lastly in this video, we're going to determine and remember how to prepare alcohols, but specifically we're going to look at diols. Diols are compounds with two hydroxyl groups. And then here are some examples of both synthetically and industrially important diols. So ethylene glycol is one, propylene glycol, and then 1,3-propane diol. So diols can actually be prepared from diketones using all of the chemistry that we just discussed in this video. So for example, you can take a diketone on the left-hand side of the scene and you can react that with H2 in platinum and you will form your diols. You can also react the diketone with lithium aluminum hydride, and then you wash your products in water and you would form the diols. And then lastly, you can react that same diketone with sodium borohydride in methanol, and you would also get the diols from there. So that's all the chemistry we've already just seen. And don't forget that diols can also be prepared through your dihydroxylation reactions, both the anti and the syn dihydroxylation reaction. And as a reminder, here's what that looks like. So you can take an alkene and you can first react it with a peroxy acid, and then you wash it with water, and that would essentially form a trans 1,2 diols. You can take your alkene, you can react that with osmium tetroxide first, and then you can wash it with sodium bisulfite in water, and you will get your syn addition of your OH groups. So you end up with a cis diol. Okay, so to cap off this video, we're going to talk about the oxidation of alcohols to aldehydes, ketones, and carboxylic acids. So recall that you can take a ketone, aldehyde, or carboxylic acid and use a reducing agent to form an alcohol. And here are your examples of the reducing agents that we've talked about. You can either use H2 under a metal catalyst, or you can use sodium borohydride or lithium aluminum hydride. And recall that lithium aluminum hydride is your really strong reducing agent that can uniquely also reduce carboxylic acids and esters to alcohols. For example, take your acetic acid and you react that with excess lithium aluminum hydride and then react the products of that with water, you're going to get this particular ethanol. But what if you want to go back? In other words, go from our alcohol to our ketones or aldehydes or carboxylic acids. Instead of using a reducing agent, this time we're going to need an oxidizing agent. So your oxidizing agents are typically chromium based. So the strong oxidizing agent that we typically would see is H2CrO4, which is your chromic acid. Your chromic acid is pretty strong, and so we typically don't just carry H2CrO4 around in a flask. We can make H2CrO4 if you take a sodium dichromate, so Na2Cr2O7, and then dissolve that in acidic water, H2SO4 in water. You will actually form your chromic acid, which will immediately start to react with your alcohols to oxidize them all the way to the most oxidized form that it can get to. But sometimes you might actually just want mild oxidizing agents. And for those, we can use a particular reagent which has a short form colloquially called PCC. It's a chromium-based oxidant, which is called pyridinium chlorochromate. It is not important that you know what that structure looks like, but you should know that PCC is a chromium-based agent. Another set of reagents that tend to go through a mild oxidizing reaction is by first reacting your alcohol with DMSO, which is your dimethyl sulfone. And then also in that same flask, you bring in COCl2, which is your oxalic acid. And then after you go through that synthetic step, you then treat it with triethylamine, which is a base, and that will take you to your mildly oxidized products. And another possible oxidizing agent is colloquially known as DMP. You treat your alcohol with DMP in CH2Cl2, and once again, you would mildly oxidize your alcohol. And so what I'm going to do for this last part of the video is to give you a synthetic map that includes all these different oxidizing and reducing agents and show you when it's appropriate to use which particular reagent. So on this scene, you have your alcohol, your aldehyde, and your carboxylic acid. Okay, so we know that we can go from an aldehyde to an alcohol if we use our reducing agents. And you can use any of the reducing agents, whether they're strong or weak, which means you can either use H2 with platinum or you can use sodium borohydride in methanol, or you can use your lithium aluminum hydride and then your second synthetic step, wash it with water. We can also go from your carboxylic acid down to your alcohol, but this time we need a really strong reducing agent. And so we would have to use excess lithium aluminum hydride and then use water to sort of get you all the way down to the alcohol. And at this point, there's really no way to stop at the aldehyde, so we can't really kind of stop there directly. We have to go down from a carboxylic acid all the way down to the alcohol. So you can oxidize your alcohol all the way to your carboxylic acid if you use the strong oxidizing agents. So in this case, you can use your sodium dichromate Na2Cr2O7 with H2SO4 and water. And remember that this is essentially just the source of H2CrO4, your chromic acid, and that's a really strong oxidizing agent. So it's not going to stop at your aldehyde, it will go all the way to your carboxylic acid. At the same time, we can also go from our aldehyde to our carboxylic acid, once again using your strong oxidizing agent. And now if you want to go from an alcohol to an aldehyde, now you use any of the weak or mild oxidizing agents. So we're looking at PCC CH2Cl2 or DMP CH2Cl2, or we use our DMSO with your oxalic acid first and then treat your triethylamine. Okay, so that's really it for oxidation of alcohols. Once again, for the oxidizing agents, you do not need to know the mechanism. You just need to know what reagents are necessary to get you all the way to your different oxidized forms.
Okay, so in this video, we have recalled some substitution and addition reactions to form alcohols. We have introduced the idea of an oxidation state to then talk about the reduction and oxidation of alcohols. We have proposed simplified mechanisms for reduction of carbonyl compounds to alcohols, and then we've also drawn out a synthesis map to interconvert between the different oxidation states of alcohols, ketones/aldehydes, and then carboxylic acids. Thanks so much for watching this video, and I will see you in class.